All right, guys, it's time for fun with math. And today we're going to continue on our journey with techniques of integration. And we're going to talk about something called integration with trigonometric substitution. But first, I want to make sure we're all on the same page with the Pythagorean theorem right here. So we basically just want to answer this question right here, which is find the missing side of each right triangle. Now, if you can just look at this and tell me what the answers are. So if you say, hey, this is just the square root of x squared plus 1, and this is just the square root of x squared minus 1, and this is the square root of 1 minus x squared, then you're good to go. If you're not quite sure how I found those, then we need to do a little bit of work. So let's look at this one here, because I feel like if you can do that one, you can probably do any of them. So the way that I found that one is I just using the Pythagorean theorem. So I'm going to call this side B. And so remember, the Pythagorean theorem says, as if I have A, B, and hypotenuse C on a right triangle, I know that A squared plus B squared is equal to C squared. And so I can use that to find this B right here. So I know that x squared plus b squared is equal to my hypotenuse, which is the number 1 squared. And so then I know that b squared then, so I'll subtract x squared from both sides. So I know b squared is actually equal to to equal to 1 minus x squared, right? So 1 squared is just 1. And then I just take the square root of both sides. And it is plus or minus, but we're going to take the plus part because we're on a right triangle. And so b is equal to then the square root of 1 minus x squared. And so here I can write b equal to square root of 1 minus x squared. And the same thing will happen here. And then the same thing will happen here. You just set up your little equation using the Pythagorean theorem, and all this stuff falls out. So we'll need to be able to do that relatively quickly. So again, if you look at these, if you can kind of see why that is, it's like a squared plus b squared equals c squared. So it's the square root of that. This one, the same idea, but now you have your a, but your b, you're missing, but they give you the hypotenuse. So it turns out to be hypotenuse squared minus that side squared. You take the square root, and similar over here. All right, so what type of integrals are we going to look at today? So we're going to do this integration by trigonometric substitution. And so what do these things look like? Well, they look like this. They typically are integrals that involve something that looks like the square root of some number plus some other number with an x squared in it. And the trick to solving these is to make the correct right triangle. And so let's make this clear by just doing a problem. So here are two examples we're going to do today. Notice I know that this is going to be a trig sub because of these square roots right here. So the square root of 1 plus x squared up here, and then down here at the square root of x squared minus 1. So that's like kind of a hint that this is a trig substitution. And then also notice I don't see a function or its derivative. So here's a function here, but its derivative is not x cubed. Right? The derivative of 1 plus x squared is 2x. So you can't use integration by substitution. Now, again, you may be able to work this out a little bit with integration by parts, but as soon as you try, I think what you'll realize is that the integral doesn't get easier. It gets harder when you break it into parts. And it's certainly not a trig integral. Right? There's no trigonometric functions in these integrals whatsoever. So how do we solve this integral? Well, the idea is focus on this and make a right triangle with that as one of its sides. So we're going to make this right triangle over here. And let me rewrite this so we have lots of space. So the integral of x cubed and square root of 1 plus x squared dx. So I'm going to make a right triangle with this on one of its sides. So I just draw a right triangle over here, which everybody can do. And I just have to figure out where this thing is going to go. And so these are going to be the legs. And so I'm going to put a 1 here. And this is going to be the other leg. So I'll put an x over here. And then this will be the square root of 1 squared plus x squared, which is just 1 plus x squared. Now you can switch out the 1 and the x and move them if you want. But if you do that, what happens is you just wind up working with trig functions that I don't like. So I always put my x over here, my 1 down there. And what trig functions do I not like? I don't really like working with cosecants or cotans. I'd much rather work with secants or tans. So I try to keep my triangles. So I'm always working with these secant or tan functions. And then between here, I have an angle theta. So this is my theta right here. And so what I'm going to do is I'm going to use this right triangle to do what we call a trigonometric or a trig substitution. And so how do I do that? Well, the idea is I want to use the two easiest sides, some trigonometric relation using x and 1 and also theta. And so this is going to come from my old friend SOHCAHTOA. And so which one of these uses the opposite and adjacent side to the angle? And that would be the TOA, right? That's what that stands for. The tan is equal to the opposite over the adjacent. So here I'm going to write tan of theta is equal to my x over 1. And I really only need to write x, but I just want you guys to see where all this is coming from. So now I know what tan of theta is. And now what I can do is I know what x is, so I know what x is in terms of theta, but now what I can do is I can take the derivative of both sides. So I'll take the derivative of tan of theta, and so that's a secant squared theta d theta, and the derivative of x is just a dx. It's really 1 times dx, but we just write the 1. And now what I can do is I can start making my substitution over here because I know what x is, and I know what dx is. Oh, the only thing I'm missing is I'm missing this guy right here. And so that's right here on my hypotenuse. And so what I want to do is look at my right triangle and try to figure out, how can I rewrite that in terms of theta stuff? And so again, you come back over here to your old good friend SOHCAHTOA, and I'll use the easiest side. So I'll use that side, and I want that side. And so which is that? That's the adjacent of the hypotenuse, so that's the cosine. So I'll write cosine of theta is equal to 1 divided by the square root of 1 plus x squared, because it's the adjacent over the hypotenuse. And then I'll just flip both sides, because remember, I really want to solve for this because I want to plug in for it. Basically, I want to do a trig substitution. So I just flip both sides here, and I get 1 over cosine of theta is equal to my square root of 1 plus x squared, which is really a secant theta. So secant theta is equal to my square root of 1 plus x squared. And now I'm going to do my trig substitution. So here I have x cubed. So I know what x is equal to. It's equal to tan of theta. So I have tan cubed theta. So it's like a note card. I flip over that x. On the other side, I have that tan theta. And then right here, I have the square root of 1 plus x squared. So over there, I know that's my secant theta. So I flip that over. So I times secant theta. And then right here, I have my dx. And my dx was equal to secant squared theta d theta. So I'll write here times secant squared theta d theta. And I'll stop here for a second, because if you look at this, everything's now written in terms of a trigonometric function, hence the name or the technique trigonometric substitution. All right, so you make this substitution using these trigonometric expressions, and then you get back a trig integral. So now we can clean this up a little bit. This is actually the integral of tan cubed theta, and then secant cubed theta d theta. And then the question becomes, how do we integrate this? Well, now that it's a trig integral, we can use what we learned with trig integrals to actually integrate this. So the idea is either work with the tan of theta stuff or the secant theta stuff using an identity. So we're going to use this identity, 1 plus tan squared theta is equal to secant squared theta. And the question is, which one do you want to solve for? Do you want to solve for the tan squared theta, or do you want to keep it solved for the secant squared theta? And so what I would think about is functions and the derivatives. So if you look at a tan theta, its derivative is secant squared theta. Well, you have a secant squared theta over here, but you're left over with the secant theta, right? So secant theta times secant squared theta. So I don't think plugging in for secant squared theta is going to work out too well. Let me think real fast. So we plug this in, and then what do we get back? Yeah, we're not going to get back what we want, right? Because derivative tan theta is secant squared theta. So I don't think that's going to work. So I think I'm going to do here, this implies I'm going to solve this for tan squared theta. So secant squared theta minus 1. And I'm going to plug this in for tan squared over here. So let's rewrite that so it makes it really clear. And so this is going to be equal to the integral of tan squared theta and then tan theta with the secant cube theta d theta afterwards. And so what I'm going to do is I'm going to replace this with what it's equal to here, and then we'll be able to make a substitution if you want, or we'll be able just to integrate this by guessing and checking. So this is actually secant squared theta minus 1, and then times a tan theta, and then you have a secant cube theta d theta left over here. So I just made this substitution. So I just turned over the note card basically, and I have this secant squared theta minus 1 on the other side. But what you want to notice is I have all these sort of secant thetas running around, and I know the derivative of secant theta. So remember, for secant theta, its derivative is what? Secant theta tan theta. So I'm going to collect together a secant theta tan theta, and then I should be able to see a function and its derivative. So this will be equal to the integral and have secant squared theta minus 1. And then I'm going to write this secant cube theta as a secant squared theta, and then a secant theta tan theta d theta. So now I see the function secant theta, and I see its derivative over here. To clean this up, I'm just going to multiply through by secant squared theta. So I have all secant theta stuff, and then its derivative on to the right of it. So this is going to be equal to the integral of what? So just multiply here by secant squared theta. So I get secant to the 4th theta minus a secant squared theta. And this is all times then secant theta tan theta. And so now if you want, I can make a U substitution, or I can do this by guessing and checking. So it's kind of up to you what you want to do. If you want to make a U substitution, my U would be equal to just secant theta, and then of course my du is the derivative, which is secant theta tan theta d theta. And so you can make that substitution, or at this point in time, I should tell you guys, it's kind of nice just to kind of guess and check. So notice, if you multiply through here by the secant theta tan theta, you get what? So times secant theta tan theta here, minus secant squared theta, secant theta, tan theta, and then all d theta. And in each one of these, I have the function and its derivative. I got the function and its derivative. So this is going to be equal to, my guess would be, all right, secant to the 5th theta divided by 5, and then minus secant cube theta divided by 3, and then all plus c. And so that's my guess, and you can check it. So notice if you check it, and the reason I divide by 5 is because when you take the derivative, what happens? So when you take the derivative of this thing, that 5 comes down, and I get secant theta to the 4th, and it's divided by 5 here, and then times the inside, secant theta tan theta. And so the 5s are going to cancel. And then the same thing's going to happen right here. So that was my guess when it checks out. Oh, okay. Now, I'm not quite done because everything here is given to me in terms of theta stuff, and theta is not x. So what I need to do is I need to go back up to my original triangle and figure out what the heck secant theta is. So let me see if I can't zoom out just a little bit here and move us around so we can kind of take a look at what's happening here. And so a little bit more, maybe a little too much. There we go. Okay, so here's my work. I'm going to come back up here and just take a look because I want to get rid of these secant thetas basically right there. And so if you come up here, I see what secant theta is equal to. It's equal to that square root of 1 plus x squared. So this is going to be equal to, and so I'm going to take the square root of 1 plus x squared. I'm going to plug it in for my secant theta. So that's the 5th power, and that's divided by 5. And then minus a square root of 1 plus x squared, and that's going to be cubed then, and that's divided by 3. And then that's plus c, and I'm not quite done. We take the square root and you raise it to the 5th power, what do you get? You actually get 1 plus x squared quantity squared with a square root of 1 plus x squared left over, all divided by 5. And then minus, if you take the square root and you cube it, you're going to get a square root of, oops, let me write the nice part first. So I'm going to get a 1 plus x squared, like a whole part, and then you get that leftover radical. So square root of 1 plus x squared divided by 3, and plus c. And that is my final answer. Okay, and oh, let me make sure. Yeah, we're good. Okay, so before we think too much, let's do this again. All right, so let's do it again. Come down here, and we're gonna look at this problem right here. So this problem, let's make some more space. I'm gonna come over here, I'm gonna write b, and I wanna do this integral. So the integral from the square of the square root, x squared minus 1, all divided by x, dx. And again, it's not integration by substitution because I'm not sure what to let u be equal because I don't see its derivative anywhere. Integration by parts, you could try, but it's going to get messier if you try to break it apart. Certainly not a trig integral right now because there's no trigonometric functions. So it is going to be a trig sub, and this is the indicator, that square root of, with x squared minus 1 underneath it. And so over here, I want to make my little right triangle. So I make my right triangle. I have to figure out, where I'm going to put this. So this minus means it doesn't go on the hypotenuse. And so it's going to be one of the legs. And then because this term comes first, it means it's the biggest thing. And so my x is actually going to go here. And then I can choose where I want to put this thing and where I want to put the 1. So I always put the constant down here, and then I'll put this square root of x squared minus 1 over here. And again, you can flip-flop these. What I just tell you, if you flip-flop them, what's going to happen is instead of working with secants and tans, you're going to wind up having to work with cosecants and cotans. And so I don't like to do that. So I just put the constant on the horizontal part right there. And then, of course, here's my angle theta. And so now what? So I want to do a trig sub. So I got to figure out what x is, and I got to figure out what this square root of x squared minus 1 is. I got to figure out what dx is. And so to do that, I just come over to my right triangle, and I just pick the sort of easiest sides here involving x. So x and 1. And so I'm going to do my old, again, SOHCAHTOA. And so which one do I choose? Well, this is the adjacent side to the angle, and this is the hypotenuse. So what's that? That's the ka. And so I know the cosine of theta is equal to, and the ka is the adjacent of the hypotenuse, so it's 1 over x. And so now I can flip both sides to get what x is equal to. And so when you flip cosine of theta, remember what happens. You actually get a secant of theta is equal to x. So now I know what x is, so I can substitute in for x. To find dx, I'm just going to take a derivative of this thing. So it's a derivative of secant theta. Remember, it's secant theta tan theta, and then d theta. And then that's equal to the derivative of x is just dx. So now I have my dx right here. So notice I have dx, I have x. And then what's left to plug in for? Right over here, I got to figure out what that is. So I come over to my right triangle, and there it is. So I'm going to choose it, and then the easiest side, which would be the number 1. And so that's the opposite and the adjacent side. And so that's the TOA. And so I know that the tan of theta is equal to, and be the opposite of the adjacent. So just a square root of x squared minus 1, all divided by 1, which is exactly what I wanted. So now I have that piece right there. So I can plug in. And so now I'll do my trig sub. So it's going to be equal to the integral. On top, I have tan of theta. So I basically turn over the note card. and I get tan of theta on top. And then on bottom, what do I have? Well, I turn over the note card on the bottom, and I get secant of theta on the other side. So secant theta. And then finally, for dx, I come down here. Here's my dx. I turn it over. I have this on the other side. So that's secant theta tan theta d theta. So there's my trig substitution. So notice all the x stuff went away, and now I just have theta stuff running around. So now I have this trig integral to solve, right? So basically the idea, you convert it to a trig integral, then we use what we learned with trig integrals to solve this. And so this one's pretty nice because that secant theta is going to basically just cancel. It's all right there. And so this is going to be equal to the integral of tan squared theta d theta. And now how do we integrate this? It's a trig integral. It's not one of my types of trig integrals, so I'm going to have to use one of those identities. And so when I see this, I'm like, oh, well, we have an identity. I know that 1 plus tan squared theta is equal to a secant squared theta. And so what I'm going to do is I'm going to solve this for tan squared theta and plug in. So this implies that tan squared theta is equal to secant squared theta minus 1. So subtract 1 from both sides. And so, you know, the idea, you have the note card, you turn it over, and there it is on the other side. So this is going to be equal to the integral of secant squared theta minus 1 d theta. These are my types. Secant squared theta I can integrate. So remember, that's just a tan of theta. So this is going to be tan of theta. And then minus. And then I can integrate 1, but now when I integrate 1, I'm integrating with respect to theta. So it's not x, it's theta. And then I have plus c. And just to make sure, let me go back to the last problem. I'll make sure, did I put plus c on this over here, guys? Did I put my plus c? Oh, yep, I did. Okay, good. I just wanted to make sure I had that plus c on there. All right, so back to the original problem that we're working here. And so now that I have this, be careful, you're not quite done because you have this in terms of theta and you want it in terms of x's. So how do I get this back in terms of x's? So what I need to do, I need to zoom out just a little bit here so I can see my little right triangle, because I'm going to go back to it and I'm going to use it because it's going to tell me basically what to do. And so here, if I want to figure out what tan of theta is, well, do I have it written down? I do. I have it written down right here. So tan of theta is equal to the square root of x squared minus 1. So it's equal to the square root of x squared minus 1. And then minus, now theta is a little bit tricky. So how do you find theta? Well, up here, you have secant theta is equal to your x. But you also have this too. You need to use either one. It doesn't really matter. So I have cosine of theta is equal to 1 over x. So you choose which one you want to use. I guess I'll use this one here because we're more familiar with cosines of theta. So I'm going to rewrite that right here so you can see what I'm going to do. So I know cosine of theta is equal to 1 over x. So how do you get rid of cosine? We just take cosine inverse of both sides. So when you cosine inverse this side, it undoes the cosine. And then you have to cosine inverse this side, always on the left. And so these will cancel basically because they undo each other. And you get theta equals cosine inverse of 1 over x. And so my theta is cosine inverse of 1 over x plus c. You could have also used this one right here, secant of theta equals x, because if you secant inverse both sides, theta is also equal to secant inverse of x. So it doesn't matter which one you use. But the trick, or where the way these are actually solved, all flies in this right triangle. So there are ways to do these types of problems without using the right triangle. But when you get stuck, it's really hard to get unstuck if you don't use it. So I always teach you guys using this right triangle, and it makes this life simpler, right? Because if you get stuck, you always go back to your right triangle, and the right triangle kind of tell you what to do. All right, so that was indefinite integrals, and now I want to do one definite integral with you guys. And so here's our problem. And so on this problem, what are we going to do? We're going to use trigonometric substitution to evaluate the definite integral, and then a graphing calculator draw a picture of the shaded region calculated. And again, how do I know this is trig substitution? Well, the square root kind of gives it away, but I can't use, again, integration by substitution because I don't see a function its derivative running around. Integration by parts is probably going to fall apart when you try to do it. It's probably going to make it more complicated. And it's definitely not a trig integral right now. So how do I do trig substitution? Again, you just make this little right triangle and you figure out where does this thing go? So now notice I have 1 minus this x squared. So this whole thing can't be on the hypotenuse because you have that minus. And so I got to decide where am I going to put the 1 and the x. And so since the 1 comes first, it has to be bigger than the x because we're working with real numbers. Take a square root of a negative number, it's going to be imaginary. So this 1 actually falls on my hypotenuse. And then next, I can decide where I put the x. It doesn't matter really, but I always put it right down there on the horizontal, and I'll put the square root of 1 minus x squared over here. And again, if you switch them, which you can do, you can put this here and that there. The only thing that's going to happen is you'll have to wind up working with cosecants and cotans. And so you can just switch them back if you want, because you may not like them, because I personally like secants and tans a lot more. And so now where's my angle? Here's my angle theta. And now I'm going to do this trig substitution. So let me erase some stuff here so we can kind of draw on here, because just so you can see the big idea. So the big idea is first we're going to figure out what x stuff is, because then that'll help us figure out what dx is. And so I choose the easiest sides, and I use my old friend SOHCAHTOA. And so this is the adjacent side to the angle, and this is the hypotenuse. And so I'm going to use the CA. And so I know that the cosine of theta is equal to the adjacent or the hypotenuse, so x over 1. And so that gives me x, basically. So now I can take the derivative of both sides. So derivative of cosine is a negative sine of theta d theta. And derivative of x is just a 1 times dx. And so now I know what dx is equal to, so I can plug in over here for that. But don't forget, I still have this square root of 1 minus x squared left over, so I need to work with this guy, and I choose, again, the easiest side. Oh, the other side's the easiest side, so I'll choose the 1. And so what is this? So this is the opposite and the hypotenuse, so that's the SO. So I know the sine of theta is equal to the square root of 1 minus x squared divided by 1. Oh, that works. And so now that I have this, I can plug in for over here, because I just turn over the note card and I get sine of theta. So this is going to be equal to the integral. So turn over that note card and I get sine of theta. Turn over this note card and I get what? This negative sine theta d theta. So I'll put that in parentheses. So negative sine theta d theta. And then don't forget, I have to change those limits of integration, because I am doing this trig sub. So don't forget to change those limits of integration. And so now how do you change the limits of integration? It's actually pretty simple. You just come down here, because here's your relationship basically between theta and x. And so these are x values here. And so we're just going to kind of go through these, like when x is equal to 0, what do we have? We have cosine of theta equal to 0. And when x is equal to 1, we get cosine of theta equal to 1. And so this top one implies what? Well, how do you solve for theta? We're just going to cosine inverse both sides. So when you cosine inverse this side, we get theta equal to cosine inverse of 1. When you cosine inverse this side, you get what? You get theta equal to and cosine inverse of 0. And so now we have to figure out what these actual values are. And so this is a little bit tricky because I know our trig's a little bit rough. So when you look at this and I ask you, what's the cosine inverse of 0? What you have to say is like, well, this isn't just anything. This is an angle. I mean, it's saying it right there, right? It's an angle. So you're looking for the angle whose cosine is 0. So basically the idea is you kind of have that unit circle and you just kind of go up on your unit circle because it starts at 1. Cosine of 0 is 1. And you're trying to figure out when is the cosine 0. And that happens right here at pi over 2. So this is pi over 2. And then if you ask me when cosine inverse is equal to 1, well, that's when the angle is 0. And so that's 0. And so my new limits of integration, I put a pi over 2 on the bottom because x equals 0 became theta equals 0. And I put the 0 on top because when x equals 1, your theta turns out to be 0. And you don't have to write this stuff here. I'm just showing right on the video so you can see what I'm thinking. So what is this equal to? It's equal to the integral from pi over 2 to 0 of negative sine squared theta d theta. And so now I have a trig integral, a definite trig integral, and I know how to work with this guy. This is another formula. So I know this trig identity, so from pi over 2 to 0, and I'll move that negative on the outside. I know how to rewrite that in terms of cosine of 2 theta. So that's 1 minus cosine of 2 theta divided by 2 d theta. Right, that's that power reducing identity. So it takes a power of sine and reduces it to a lesser power, but using the cosine of 2 theta. And so then that's going to be equal to, I guess I'll move that minus through again and kind of clean this up. So this is going to be the integral of pi over 2 to 0. I can put this 2 over here, so I get negative 1 over 2. And then a minus will be a plus cosine of 2 theta, all divided by 2 d theta. And now I'm going to integrate this. So I can integrate negative 1/2. And remember, I'm integrating respect to theta. So what I'm going to get here is negative 1/2 theta. And then plus, my guess would be sine of 2 theta divided by 2. I'll put plus c here. But I'm going to be off a little bit, guys. So when you check this, what happens? So what's the derivative of sine? It's going to be cosine of 2 theta, and it's still divided by 2. And then don't forget to multiply by the derivative of the inside. So those 2's wind up canceling. So I'm missing a 2 on the bottom. So instead of dividing by 2 here, I have to divide by 4. So when these cancel, I'm left with a 2 on the bottom. So it's just a guess in check. But I don't need to write plus c, right? So that's my little mistake because this is a definite integral. So I need to write evaluated from pi over 2 to 0. And now I can just do what it says. And so right here, I'll write equals. And I'm going to plug in my 0. So I'll go nice and slow here. So negative 1/2 times 0 plus sine. And again, I'm going to plug in 0. And 2 times 0 is 0. So sine of 0 divided by 4. And then minus. And so in parentheses, now I'm going to plug in pi over 2. So negative 1/2 times pi over 2. And then plus, I'll plug pi over 2 into here. And when you multiply 2 times pi over 2, you get sine of pi. And that's divided by 4. Okay, and now we just got to simplify this, right? Do the arithmetic. So that's going to be a 0. Sine of 0 is 0. Sine of pi is 0. And I know this from the unit circle, guys. So it's like sine of pi is over here. It's the height because sine is the output. And so it's height 0. And so then I have a negative and negative. So negative and negative is a positive 1/2. And then times pi over 2. Oh, and that's just equal to pi over 4. And so my answer should be pi over 4. And so now we're going to check this. So let's check it. And so we'll check it with our graphing calculator. So if you have a graphing calculator, take it out. And maybe I'll zoom out here a little bit first, just so we can get this all on the screen here. And so let me see if I can move this around. And so you can see the whole problem all at once here. So there it is. And I'll take out my graphing calculator, and I just want to graph the original function. So I'm going to graph this thing. I'm going to graph this thing right here, guys. So make sure you're graphing the original function. So on my calculator, I turn this on, I hit y equals. I'm going to type in the square root of 1 minus x squared. So there's x squared. I'm going to make my window go from my limits of integration at first, so 0 to 1, knowing that if I have a problem on the graph when I try to calculate that integral, I can always make the window bigger. So 0 to 1, and then I'll zoom fit it. So go down to zoom fit and hit enter. And so we can see what that graph looks like. So it starts up here at some height, looks like probably height 1, and then it heads down. So we can trace this little graph here. So I can draw a little graph. So I'm going from 0 to 1, goes up and comes down. So I know what it's going to do. It should shade in that region. And the question is that region, that shaded region, is that pi over 4? And so we'll hit second trace to pull up the calculate menu, go down to number 7, hit enter. So my lower limit was 0. My upper limit is 1. I'll hit enter again. It shades in that region there and returns this number 0.785. So 0.785 ... goes on, probably forever and ever. And then the question is that actually pi over 4? So let's just check. I don't know what pi over 4 is, so let's just check it out. And so second quit, second pi, divided by 4. At least it's still positive, right? And it is. It's the same number, so I don't think it's right. I know it's right. And that ends the lecture on trigonometric substitution.